Hello, Dr. Shahab. I'm Sarah Abdallah. I'm going to be presenting floating point operations, specifically addition and subtraction. First of all, to add or subtract two floating point numbers, there are multiple steps that we have to follow. We have to make sure that both numbers are normalized, make the two exponents the same, add or subtract the significance, see if there's an overflow or an underflow, and then normalize again if necessary. Suppose you want to add these two numbers, x equals to 0.5 in base 10 and y equals to 0.372 in base 10. The first step to do is to convert them into base 2 binary. The second step is to normalize them, so to put 1 point something times 2 to the power something. So x will be equal to 1 times 2 to the power minus 1, and y will be equal to 1.011 times 2 to the power minus 2. Then for the third step, we compare the magnitude of the two exponents. They should be the same. Here they're not the same. One is 2 to the power minus 1. The second one is 2 to the power minus 2. So what we do is we take the smallest exponent, which is 2 to the power minus 2, and we have to transform it into minus 1. So we get 0.1011 times 2 to the power minus 1. Then for step 4, we add the significance. So we get 1 plus 0.1011, and we'll get 1.1011 times 2 to the power minus 1. And we check if there's an overflow or an underflow. Now, how can we do this? Both overflow and underflow can't be represented. Now, we see if our integer is at the max end or the min end. Here it's just 2 to the power minus 1, so it's neither an overflow nor an underflow. Now for the final step, if necessary, we normalize the final answer, but here it is already normalized, so we don't do anything. Now by adding 0.5 plus 0.372, we should get 0.872. But what we got from the previous slide is 0.84375. The reason for that is that 0.372 in decimal actually has an infinite repeating representation as a binary fraction. So it's supposed to be 0.10111, 110, and so on forever. And that's why we rounded it to 0.1011. Now suppose you want to subtract these two numbers, x equals to 0.5 in base 10 and y equals to 0.4375 in base 10. The first step is to convert into binary. So we get x equals 0.1 in base 2 and y equals to 0.0111 in base 2. Now for the second step, we normalize like we did before. So we'll get x equals to 1 times 2 to the power minus 1 and y equals to 1.11 times 2 to the power minus 2. Now for the third step, we should make sure that they have the same exponent, which they do not. So y will be equal to 0.111 times 2 to the power minus 1. And as we know, doing a minus b is like doing a plus minus b. So the subtraction is actually an addition. Now we can subtract the significance, so we do 1 minus 0.111, which gives us 0.001 times 2 to the power minus 1, and there's no overflow or underflow. Finally, we normalize the final answer if necessary. Here it is necessary, so we'll get 1 times 2 to the power minus 4, which is 0.0625, which is indeed 0.5 minus 0.4375. Now we need some hardware to be able to do this using a machine, because we're not going to do this step by step. It takes a lot of time and it's too slow. So we use the floating point addition hardware. First of all, we have two numbers in floating point format, and when we're done, we'll get the final sum or the difference also in floating point format. Then the exponents go to a small ALU that figures out who is the smallest exponent. Then it denormalizes it, in order to get the same exponents for both numbers. Then it's going to go to a control unit, which is going to cause some change in the exponent as well as some shifting in the value. After that, it goes to a shift right unit. And as you can see above this unit, we have two multiplexers. Both are 2 input, 1 output multiplexers. The first multiplexer chooses one of the two fractions to do a shift on. And of course, it's going to choose the one with the smallest exponent. Then it takes the second fraction, the one with the bigger exponent, and we put both fractions in the big ALU. We know that the small ALU does the subtraction of the exponents. Now the big ALU is going to do either addition or subtraction of the significance or the mantissa values. It depends on what we need. After all that, it sends the result into another multiplexer. We can see that another value enters 2 in the multiplexer. It's the rounding hardware. Then we shift to the left or right, where we are renormalizing. Also, we have to increment or decrement the exponent. Finally, we apply the rounding algorithm, which gives us the fractional part and the exponent part. If it's denormalized, we do all the loop over again. If not, we're done. Thank you.